In this last video about addition reactions, we'll talk about oxidation of alkenes. In the previous videos, we've talked about adding different atoms X and Y across double bonds. Those can be hydrogens or oxygens or halogens. In this video, actually, this might be hard to see in some cases, but both X and Y will be oxygen atoms. And there's lots of different products actually that can have both X and Y be oxygens. Some of those things are going to be called diols. Some of those things are going to be called epoxides. And in some cases, we'll get new carbon-oxygen double bonds. So we'll be talking about epoxidation, dihydroxylation reactions, as well as ozonolysis reactions. Okay, there's a lot going on this slide. So what can happen when you treat an alkene, like cyclopentene in this case, with a per acid, which can be represented by lots of different, remember, a carboxylic acid looks like this. A per acid has an extra oxygen. So instead of an OH, this is just a carboxylic acid, a per acid is going to have an extra oxygen. And this oxygen can readily be transferred to carbon-carbon bonds. We said earlier that this oxygen-oxygen bond is very, very, very weak. So what can happen is that the alkene can attack that oxygen, the extra oxygen in your per acid. What happens then is that you break the oxygen-oxygen bond, and then to avoid forming 5 bonds at this carbon, the pi bond can act as a base to attack this hydrogen, and this pair of electrons can form a new oxygen-carbon bond, and what we get is a 3-membered ring containing an oxygen, which is called an epoxide. So whether or not you know the mechanism, I don't really care. What I do care about you knowing is that alkenes react with per acids, most often peroxyacetic acid or metachloroperbenzoic acid, which is often abbreviated as MCPBA. When you see either one of these reagents, you want to think that you're going to be forming a 3-membered ring containing an oxygen, which is called an epoxide. Notice that since all these bonds happen simultaneously, then we're going to have a syn product, meaning that both bonds to the oxygen are on the same side of the ring. So we could also have drawn it where they're both down to the oxygen. Those are the same compounds in this case. Okay, so what can be confusing, so I don't want you to be confused about this, is that there's different ways of drawing epoxides and there's different ways of writing these per acid reagents. So if you see MCPBA, or if you see RCO3H, or if you see this kind of nomenclature, all 3 of these are per acids, so you just want to think epoxidation, right? So these are 3 different ways of saying the exact same thing. We're just epoxidizing an alkene, right? Remember that it's a syn addition, so the stereochemistry of the alkene is important in determining the stereochemistry of the product. So let's draw the product from this reaction, right? We're going to add an oxygen to both of these carbons. We're going to get a 3-membered ring, and we're going to have both bonds up, right? So another way we could draw this, which can be confusing, is we could make these 3 atoms in the plane. So we have an oxygen, carbon, carbon, oxygen. So if we tilt the molecule back, that's going to push this methyl group up, and that's going to push that methyl group back. So notice that the trans alkene gives a trans epoxide, even though it's a syn addition, right? Because the oxygen added to the same side of the alkene, right? But the methyls were on opposite sides of the alkene, so the methyls are going to be on opposite sides of the epoxide. So these are 2 different ways of representing the same molecule. Don't be confused by this. But in this case, if we start with a cis alkene, right, we could draw the epoxide like this. But now if we tilt it back into the plane of the page here, both of the methyl groups are together, So we're going to get a cis epoxide in this case, right? So a cis alkene is going to generate a cis epoxide, meaning the two methyls are together. A trans alkene will generate a trans epoxide. In both cases, though, we have a syn addition of oxygen to the alkene, as the oxygen's adding to the same side, to both carbons from the same side. So we could draw them like this or like this. In the last case, right, this is very similar to the previous slide. We just want to draw the fact that both bonds to the oxygen are happening from the same face of the alkene. If you want to draw in the hydrogens, you could do so as well. Okay. An added complication of epoxides is, remember, just like in a bromonium ion, these things are really, really strained, and they can easily undergo nucleophilic attack by a nucleophile. And in this particular case, we're going to use acid and water to activate the epoxide. So if we treat an epoxide, these things are stable, and we can isolate them. Unlike a bromonium ion, we cannot isolate. An epoxide, we can isolate. We could isolate this compound, and then we can subject it to dilute acid. And what we're going to end up with is a transdiol. We're going to actually end up with two transdiols, right? One from the water attacking this carbon, which would give us this product, and one from water attacking this carbon, which would give us this product. Let's look at the full mechanism in order to understand this. Let's look at the mechanism here to understand why we get an antidiol from this series of reactions. So if we have an epoxide here, and let's draw it flat, just maybe this might make this a little bit more clear here. We have a flat ring. We've added the oxygen to the same side of the alkene to get an epoxide, right? This oxygen has two lone pairs of electrons, so it can react with the hydronium ion. In an acid-base reaction, this is the basic site, so the proton's going to get transferred to this oxygen atom. And now, this is a much better leaving group because when it leaves, it's going to be neutrally charged. In the top example, water acts as a nucleophile and it attacks this carbon, but either carbon could get attacked. If we attack this carbon, we get this transdiol. So I'm going to draw the other carbon being attacked. And so now we break this carbon-oxygen bond. Water comes from underneath. So let's draw, I think it's really helpful to think about the structure that we get here. This bond still exists. So we have an OH up here from this bond breaking. So this was our leaving group. It's still attached though. And going down, we have the water molecule that attacked from the opposite side of our epoxide. And then all we need to do is transfer a proton from the product to another molecule of water, so the water can accept this proton to give us the enantiomer of the product that we got at the top. So we're going to form a mixture of both of these enantiomers. But understanding the mechanism hopefully allows you to understand why, if you start with a syn or cis epoxide, you get an anti-diol. Diol meaning di-alcohol. Okay, so if you don't want an anti-diol, what you would probably want to do is dihydroxylation or Syn-dihydroxylation with this reagent, which is called osmium tetroxide, which is often just written like this, OSO4, osmium with 4 oxygens. In this case, you have simultaneous addition of both oxygens through this kind of a mechanism. And so it's a syn addition. The problem is you still have this osmium atom there. So in a second step, you get what's called hydrolysis. So you break the osmium-oxygen bonds and you replace them with hydrogens. So you get a syn-diol in this case. Let's look at some examples of formation of these diols because I don't want you to get tripped up by this. It can be somewhat confusing. So remember, what we were showing before is that sometimes you can epoxidize an alkene and then hydrolyze it with dilute acid. We can represent epoxidation with this reagent or this reagent or this reagent. We can represent dilute acid by either H3O plus or the combination of sulfuric acid and water. So if we look at each one of these problems, right, if we epoxidize this guy, right, what we're going to get is something that looks like this. We had a syn addition of oxygen to the same side of the alkene, and then, so this is an intermediate that forms after step 1. When we take that and we treat it with hydronium ion, right, the water is going to open this thing from the opposite side, so we're going to have one OH up and one OH back. So we had an anti-diol that formed from our alkene, right? So let's look at the same series of reactions, but if we start with a trans alkene, we get an anti-diol. If we start with a cis alkene, the epoxide intermediate that we formed will look like this kind of. And then we treat that with dilute acid. And what we're going to get is water attacking here. So we have this OH up, for example, and we'd have this OH back, right? But this bond can rotate, and the way that we usually represent these things is with the staggered kind of conformation. So this is the same as this product, right? We just rotated around the carbon-carbon bond. So what can be confusing in some cases is that anti-diol from a cis alkene is actually a cis diol if we draw it in this conformation. What can be a little bit easier to see is if we start with a cyclic compound, we're going to get always the trans diol in this case. Okay, so that's epoxidation followed by ring opening. These are anti-diols. So this is what you want to do to make anti-diols. Let's say we wanted the syn-diols. We just talked about that. What we'd want to do in those cases is treat them with osmium tetroxide followed by hydrolysis. We can do this catalytically as it's with NMO as a stoichiometric oxidant. You want to think about all these as the same set of conditions, which gives us a syn diol. So in this case, right, we're going to have both OHs adding to the same side of the alkene. So notice now in this case, we get the syn product. In this case, we also get the syn product, right? So we have OH up, but we can again rotate around this bond. So we could draw it in either this conformation or this conformation. And in the last case, now we have the syn diol where both OHs are on the same side of the molecule. The last reaction that we're going to talk about is ozonolysis. It has a complicated mechanism that I really don't want to go into. So the easiest way to understand ozonolysis is that it's also an addition reaction where oxygen is added to both carbons of our alkene, right? But what happens is not only do we break the pi bond, we break both the pi bond and the sigma bond between the two carbons, and we add an oxygen to this carbon and we add an oxygen to this carbon. So you end up breaking a carbon-carbon double bond and you form two new carbon-oxygen double bonds. So the easiest way to think about this is just break your carbon-carbon double bond and replace it with two carbon-oxygen double bonds. The trickiest version of this kind of reaction is when you have a double bond in a ring, right? You're going to break that double bond and replace it with two carbon-oxygen double bonds. There's a hydrogen here, and so we can also draw this as a 1, 2, 3, 4, 6, 7. So if this thing unravels, what would it look like? 2, 3, 4, 5, 6, 7. Where this would be carbon 1, 2, 3, 4, 5, 6, 7. So these are two different ways of representing the same molecule. Notice that if you have a double bond in a cyclic alkene, you're going to get two carbon-oxygen double bonds in the same molecule. If it's acyclic, they're going to be two carbon-oxygen bonds and double bonds in two different molecules. Okay, so let's talk about all the different ways that you can add two oxygens to an alkene. One way would be epoxidation, followed by ring opening to give you a dihydroxylated product. So these are anti-diols. If you use osmium tetroxide, you form an osmate ester, which can get hydrolyzed to give you a syn addition. Since both bonds to the oxygen happen simultaneously, that's a syn addition. Ozonolysis completely cuts the carbon-carbon double bond, and you get two new carbon-oxygen double bonds.